Hello, everyone. Thank you so much for coming out to our third iteration of this Distinguished Speaker Series. This has been put on in collaboration with the Society of Mathematics in Mexico. And today we are thrilled to introduce our speaker. Today we will be hearing from Dr. Amanda Montejano, who is at the National University of Mexico. Just a few quick reminders. We are recording this meeting and it will be available on YouTube. So welcome to any of those YouTube people. Please feel free to send out the information for our future seminar series, our Distinguished Speaker Series, and our regular colloquium series. All that information is available on our website. If you have any questions, please feel free to pop them in the chat or ask at the end of the talk with the video off. And yes, whenever you are ready, Dr. Montejano, please take it away.
Thank you very much, Erin. So let me, let me share my screen. There is, can you see my screen now? Perfect. Okay, thank you very much for the invitation. It's an honor for me to be here and talk about this work, which I really like. This is a joint work with Yair, Caro, and Adriana Hansberg, with whom I have worked for 7 years now, I think, and whom, well, I thank for sharing all these mathematics. We've been learning together a lot and developing along those years the ideas and the techniques that leads us to this work. It is a work that lies between Ramsey theory and extremal graph theory. So the outline of the talk will be this. I will start by talking about Ramsey theory and its philosophy. Ramsey theory, roughly speaking, is like the study of the existence of monochromatic structures in colored universes, mathematical universes. So after that introduction, I will talk about some other patterns, color patterns, besides the monochromatic ones, that could be unavoidable under certain specific suitable conditions. Then I will talk about the extremal graph theory, and I hope there you will see the connection. After that, I will present our contributions, and finally, I want to talk about the one of the most important tools that we use to prove large of several of our contributions. This is a technique called dependent random choice, so I will talk about this at the end of the talk. So let's start with the Ramsey theory. Ramsey theory is a beautiful branch in combinatorics. Here you have a paper, which is more like a white audience paper. It's kind of old, but it's, in my opinion, it's a very nice introduction if you want to know more about Ramsey theory. The authors in this of these papers, Ronald Graham and Joel Spencer, they said that this the brilliant mathematician Ramsey, who is here, proved that complete disorder is an impossibility, and this is a typical way to present Ramsey theory, like in for white audiences, and particularly that in every large set of numbers or points or objects, so in every large mathematical universe, if this universe is really large, then you will necessarily find some highly regular pattern. So this is the main idea in Ramsey theory, to recommend you most current reference. This is a podcast called the Ramsey Theory podcast, where many people working from the Ramsey Theory community talk about their experiences and their work. So this podcast was made by some students in Simon Fraser University, and is called No Strangers at This Party, because the most particular way, or the most common way to introduce Ramsey theory in undergraduate levels is with this fact, or with this sentence that states that in any party with 6 or more people, there are either 3 strangers or 3 non-strangers. So the situation can be depicted in a graph, or more precisely as a 2H coloring of a graph. But you can imagine that the vertices are the people, and then red edges indicate that those 2 people are strangers, and blue is the other way. So the statement is in a mathematical language that if n is greater than 6, greater or equal than 6, then any 2H coloring of the complete graph of order n will contain a monochromatic triangle. That is the fact that 3 people is either stranger or non-stranger. I want to emphasize, this is easy to prove by using the Pinjol principle, but I want to emphasize in this fact that we really need to have the universe, the mathematical universe, which in this case is the set of edges of the complete graph, to be large in order to imply the monochromatic triangle in this case. Because observe that if n is not large enough, in this case, if n is equal to 5, then you can find a 2H coloring, at least. Here is an example where no more monochromatic triangles are present. So this hypothesis of condition is very important in Ramsey theory. It is actually the one that determines the Ramsey parameter in general. Here you have a statement which is a little bit more general than this. This is sometimes known as the baby Ramsey theorem. Here you have another one which is not the general Ramsey theorem, but it's a particular case, but it's a little bit more general than the baby one. And here I want to, again, emphasize on this parameter, which is the smallest, given you can choose any positive integer t. Instead of triangles, we are going to find or to prove the existence of monochromatic copies of a complete graph with t vertices, and t can be any positive number. So for any t, there is a minimum integer, smallest integers that we are going to call like this, such that if the complete graph that I'm going to color is large enough, which means if n is larger than this parameter, then any 2H coloring will contain the monochromatic thing that I'm looking for. Okay, for just to say, the real baby Ramsey theorem is, in my opinion, not this, is actually the Pinjol principle. If you study the general Ramsey theorem statement, and you pick or you choose the simplest values for this term, you will find that the pinyon principle is like the seed of this theory. So the whole Ramsey theory is like a wonderful word that borns from the pinyon principle, which is really a very useful and simple principle. No, so now let's talk about the subject of the talk, which are unavoidable color patterns besides the monochromatic ones. Okay, we are going to focus for two colors. Ramsey theory can be stated for more than two colors, but in this work we are going to fix our mind just with blue and red. And we are going to color, as I said, so the edges of the complete graph. So the universe that we are working in is going to be the set of edges of a big, really big, large, complete graph. By Ramsey's theorem, we learn that monochromatic patterns are unavoidable. And we ask ourselves, or it's natural to ask, which other color patterns that are non-monochromatics can be unavoidable as well. Of course, the answer to this question is known, because if we want to consider all 2H colorings, then we have to consider the red coloring of the whole big complete graph and the blue monochromatic coloring. So in there will be no other thing than monochromatic substructures. So we need to avoid those colorings. We need to think in colorings that really have different enough edges of each color. So the right question here is to ask the following: which colors patterns, besides the monochromatic ones, are unavoidable in every 2H coloring, but with two restrictions? The first thing is that we need to have n large enough. This is the Ramsey type parameter that we talked before. We need the universe to be large enough. But here, where we are looking for non-monochromatic patterns, we need to take into account another parameter, which is how large the edges or the color classes of it, the edges of each color, or the color classes, how large they have to be in order to imply or to force the existence of those color patterns. If they are, but because who says that there are other color patterns that are unavoidable besides the monochromatic ones? So who says? Well, Bollobás conjectures that yes, that there are other color patterns in every 2H coloring of the complete graph, with a positive fraction of edges in each color. So remember that the number of edges of a complete graph of order n is n choose 2. So a positive fraction, we can think here of any positive fraction. To fix ideas, just think in 1/2. That is, we are going to work with colorings that have exactly the same number of red edges than of blue edges. In this case, if we restrict ourselves to this type of colorings, which are kind of a balance, what color patterns can we we say that are unavoidable? Observe that we need to take into account all coloring with this characteristic. In particular, there are two important colorings of the whole graph that needs to be taken into account, which are these ones. And any pattern that we wanted to prove that is unavoidable needs to live here, or to be to live there. We need to find it in these two particular colorings. So it happens that Bollobás conjectures from 2008 was that for any epsilon, so you can fix the positive fraction that you are going to have in all your colorings, and any t, there is a moment. So for large enough n, any 2H coloring of the complete graph with at least that positive fraction of edges in each color, so with at least epsilon times n choose 2 edges in each color, will contain a copy of a complete graph, this time of order 2t, with one of the following patterns. Either there are I will be able to find either a copy of 2 K2T, where one color induced 2 complete monochromatic graphs, and the other color induced a complete bipartite graph, either in this blue and red, or in this red and blue pattern, or this other structure, which is as you can see in the slide. So this conjecture was proved. Sorry, I want to say something. All the illustrations, these beautiful pictures that you can see here, were made by Adriana Hansberg, and she generously shared it to me. So all those illustrations were made by her. So the conjecture, Bollobás conjecture, was confirmed in the same year by Cutler and Montágh. So what they proved exactly? Let's exactly what I said. Let's see it again. Is that for every epsilon, so you can between 0, a positive epsilon between 0 and 1/2. So you can think on this epsilon as the positive fraction that you have from each color, and any non-positive integer t. There is a smallest integer. This parameter is the Ramsey type parameter of the problem, such that if n is large enough, which means that, then any 2H coloring of my complete graph, which is large enough, with at least this amount of edges in each color class. This is another parameter that the one that we are going to be focused on. Then this will coloring, any of this coloring will induce a monochromatic member of a family. Here I change a little bit the language, but remember I put here we can talk about color patterns like in the picture, or induced monochromatic graphs. If you can notice that the graph that induced, for instance, here, red edges, is a complete bipartite graph KTT. This is an induced red KTT. This is an induced blue KTT, and the other graph is called the split graph. It's a graph with a complete graph of order T, an empty graph of order T, and all edges between those set of vertices. So this one here is an induced blue STT, and this one here is an induced red STT. So what another thing that I want to change here in order to show you our contributions is that remember that n over 2, which is the number of edges in a complete graph of order n, is roughly n squared over 2. So we can think of this result as sorry, a quadratic amount of edges in each color class. By this, I denote the number of red edges in my 2H coloring. Those are the number of blue edges in my 2H coloring. If both of them are greater than some constant for times n squared, then we will have the existence of some induced monochromatic member of this small family with two members, the bipartite complete graph and the split graph. So we really don't care about the Ramsey type parameter, which is the size of the universe, and also we really don't care about the precise constant. We only are going to care in this talk about the order of magnitude of the number of edges here, which in this case is quadratic. So here I put again the theorem by Cutler and Montágh. It's that a quadratic amount of edges in each color class will force the existence again of an induced monochromatic member of this family. So, but what we asked was, do we really need that much edges in each color class? Can we imply the existence of those induced monochromatic graphs with less than a quadratic number of edges? Remember, this is always if n is large enough. We are not going to care about the Ramsey type parameter, which is how large is this n. Well, in 2021, we were able to prove that in order to prove the induced monochromatic member of this family, the induced monochromatic pattern that I show you, we really don't need a quadratic amount of edges in each color class. We need a subquadratic. So we prove that there exists a function depending on t, such that this amount, which is subquadratic in terms of n, forces the existence of those color patterns that we are studying. Short after this, Antonio Girao and Bhargav Narayanan, they proved that actually this function, depending on t, which is notice that it's not depending on n, it's only depending on t, is exactly 1 over t. And they also proved that this is best possible condition to the veracity of the well-known Kovaresos-Turan conjecture. So in order to tell you what is this conjecture, let me go to the next part of the talk, where I will explain a little bit of extremal graph theory and present some very classical results in this area, and try to establish the connection between Ramsey theory and also our work. So for now, forget about colorings, about 2H colorings of the complete graph. We are going to think now on graphs, just on graphs that are dense. We want to study or to know what structures or subgraphs are implied in a graph in terms of the density of the number of edges, in terms of the of how dense it is, the graphs. So fix an n and think on a graph of order n. Then choose a positive integer t, and what a classical theorem by Turan says is that there is a constant in terms of n. It's a function of my t, but it doesn't depend on n, such that if the graph, which is of order n, has a lot of edges, that is a quadratic amount of edges, then necessarily the graph will have a complete graph of order t as a subgraph. So this theorem is in some sense like the counterpart of Ramsey's theorem, the one that I present you at the beginning, but in the world of extremal graph theory. It doesn't, you have to, it's not hard to see, to think about, I mean, it doesn't imply the Ramsey theory and vice versa. It doesn't imply, but it's close related. In this case, which is the origin of the theory, the constant and it's precisely known in terms of t, and it is also known that this is best possible. So the extremal parameter, it is determined for each t exactly, and everything is beautiful. There are other problems in extremal graph theory where we want to know how much edges or what amount of edges in a graph of order n we need to imply, for example, the existence of a complete bipartite graph, other graphs which are not the complete one. So again, it is known that for a fixed positive t, there is a constant, another constant, sorry, this is each problem has a different constant. So this c and this c are different. I just want to emphasize the order of magnitude that we need to force some structure, not the precise constants. So here, look, this is a Kovarisov-Turan theorem. We can imply the existence of a complete bipartite graph with this amount of edges. And the conjecture is, again, that this is best possible, but it is a conjecture that is, it's believed to be true, but is not published. So there are many other statements or beautiful theorems in extremal graph theory, where again the flavor is to know how many edges imply the existence of particular structure that or subgraphs that we are interested in. For example, an old result from Erdos and Galay state that with a linear, again, remember all those constants are different. So I don't care. I just want to see the order of magnitude. So a linear amount of edges in a graph of order n implies this matching. So this copy of a t times an edge, a complete graph of order 2. And this is also an interesting one. This is actually a very particular case of a theorem which is from Erdős and Radó, which is stated in sets of systems or regular hypergraphs with the edges of the same size. In the case where we have edges, simple graph with the edges of size 2 or order 2, then this is known in literature as the sunflower theorem or some other as delta systems. So in the particular case where we are in simple graph, it says that a constant amount of edges in a graph of order n, and of course this constant depends on t but not on n, then we can imply the existence either of one of either two structures, or this matching with t edges, or a star with again a star of order t. Okay, so coming back to our work on unavoidable color patterns in 2H coloring of a large complete graph, let's summarize what we know up to now is that no restriction imply only an induced monochromatic complete graph. This is Ramsey theory. A restriction of or subquadratic order like this, a constant times n squared minus 1 over t, this will imply an induced monochromatic graph in this one of those two graphs, which are the bipartite complete graph with t vertices in each size, or this split graph that I showed you. So this was the Cutler and the Girao and Adriana result. But we want to know what happened with other amount of edges. What color patterns are unavoidable under these conditions, or what set of graphs can we find necessary with as an induced monochromatic subgraph in every 2H coloring of a very large complete graph with this amount of edges in each color class. So we to present our contribution, we generalize this theorem by providing like a non-symmetric, I will explain now, non-symmetric version of it. And this was like by taking the technique, taking the technique and working on and seeing what is the most that we can obtain or get with this technique. So in our results, we are going to take 3 parameters, so 3 positive integers, r, s, and t, with r needs to be greater or equal than 2, and then t, think of s as a smaller integer than t, but t needs to be greater than 2 as well. So what can we prove? We can prove that there is a constant depending on these parameters such that, again, if n is large enough, remember that here we implicitly have Ramsey type parameter on all these problems that we are not working on. We are only focus our attention in the theorem type or extremal graph, extremal parameter, which is the size of the of both color classes or of the minimum color class. So if my universe is large enough, which is the set of edges in a complete graph, then every 2H coloring of it will, with this condition, will produce or will imply the existence of an induced monochromatic member of this family. So this is maybe a little bit technical. It's just like that we take the technique and go further and further until what I don't have pictures here, but remember that Girao, at the beginning, Girao and Adriana proved that this amount of edges will imply an induced monochromatic member of this, and the picture is here. This is the picture. Then we were able to recover this theorem, but we prove a little bit more because we have this parameter here. Remember, S can be smaller than T, and then here this number, this amount is a big number depending on T. And here we have again the split graph of with T vertices in each size. So if from this, I mean, this first statement is our main theorem. From here, we can deduce, for instance, when taking S equals 1, we obtain a statement where we imply with a linear amount of edges in each color class an induced monochromatic copy of a big star. Remember, what is this? This is a complete bipartite graph where one side has only one vertex and the other side is a big number in terms of T. So this is a star, a big star, or our split graph of with T vertices in each side. Also, with a constant number of edges, we were able to prove the existence of an induced monochromatic member of this family of 3 graphs. So instead of have a big star and the split graph, we can guarantee the existence of a split graph, monochromatic induced split graph, or a complete graph where which is unbalanced, a complete bipartite graph which is unbalanced, where we have a part with S vertices and the other part with T vertices. And remember, S can be smaller than T, and or a matching, where here is the first time that the air plays a role, matching of R copies of a complete graph of order 2, which is an edge. So again, remember that each problem has its own constant, and the constant here depends on the parameters that we are choosing. And again, in this work we didn't work hard on specify the constants in terms of of R, S, and T, but on seeing the main term of the bound in terms of N. So here we have two different results with a linear amount of edges. Those are unavoidable 2H color patterns that appear with this amount of edges. And finally, for a constant of edges in each color class, we can prove that if N is large enough, then we can find a monochromatic, induced monochromatic copy of a matching with R terms, and or a star, again with the parameter T here. So all these bonds without seeing the constants, how do you say, without seeing the constant, all these bonds are in the order of N, are best possible. And now is work in order to see if we can improve the constants. But to finish, I want to, as I told you, I want to talk a little bit on the one of the main tools or techniques that we use in this work. This is a technique called dependent random choice. It's a probabilistic technique that were used by several authors in different manners until in 1911, Jacob Fox and Benny Sudakov kind of compiled the whole ideas and developed the whole technique now known as dependent random choice, like in a very structured way available to many others to use it. So it is a very, very powerful technique. We use just a simplified version on the whole version. It is very useful in extremal graph theory, in additive combinatorics, in Ramsey theory. So it's like really a big hammer to work with. The lemma that we use is very simple. The main idea is that what can you imply, again in extremal graph theory, what can you imply if your graph is dense enough? So think about a big number k, big integer k, and a small integer s. So you can choose k and s as you want them, but think about k really big and s not too big. Then the dependent random choice said us that there is a constant, again, it's the same structure that we are working with. There is a constant such that any graph of order n with that quantity of edges at least, and again you can observe here that we have this n squared n to the 2 minus 1 over s, where s is this parameter that we choose. So if the graph has that much edges, then we can imply that there is a big set of vertices. Remember, k is the big number. There is a big set of vertices x with a very, very nice property. The property that each subset in x of size s, which is the small number that we choose, then this y will have a common neighborhood of size, again, k. So a really big common neighborhood. I will show you pictures in a moment. So this tool is a probabilistic tool. It's actually not so hard to prove it, but it's really very powerful. So how do we use this lemma in order to prove our theorem as follows? Remember that we want to prove that. So I want to show you an idea of how to prove this first sentence. So how to prove that with that amount of edges in each color class, we will force the existence of an induced monochromatic member of this family. Okay, so we will use the dependent random choice. We have T and we have S. So we need a constant that we will infer from the dependent random choice by taking S, the small parameter equals S, and the big one is going to be the Ramsey number of the bipartite Ramsey number of T plus 1. So, why is that? Because of the following. We will consider any 2H coloring of a really large complete graph. Again, here, I'm not wondering about how large is N. I know by the dependent random choice that if N is large enough, I will find this constant with this property. So if N is large enough, I will have a 2H coloring where I can apply the lemma to each one of the graphs induces by the color classes. So to the red graph induced by the red edges and to the blue graph induced by the blue edges. Because I have enough edges in each of those graphs, I can make use of what my dependent random choice lemma said me. So here, if I look at the blue graph, I will find a big but really big subset such that each S, so this big is size K and this small is size S, such that each S here will have a common blue neighbor, which is really big. But because here I have enough edges, I apply Ramsey's theorem, and I can find a set which is monochromatic. And so then, and the same thing I can do with the red graph. The thing is that because, so here I have a monochromatic thing, here I have a monochromatic thing, and because of the neighbors are so big, of course there are technical details to handle on, but this is the main idea. But because of the neighborhood is so big, I can find again a really big monochromatic thing here and a really big monochromatic thing here. Then you have to make a case analysis because you know this one and this one here, which I didn't draw, is monochromatic, but you don't know if it's red or blue. So you have to make a case analysis if this is red and this is blue, or this is in the other way, blue and red, and you end up finding the patterns that you want in all cases, but this case that both are blue in the blue thing and both of those are red. So in this case, you cannot imply the patterns as easy as in the other cases, but you remember that this big monochromatic clique here is of size the bipartite Ramsey number. And again, this one is as big as the bipartite Ramsey number. So in between them, there must be a bipartite monochromatic graph. So, and this will end the argument in order to prove this particular result. And thank you very much. This is all.
Thank you so much. Let's go ahead and thank our speaker. Great. Thank you so much for that great talk. I'm going to go ahead and end the recording here. If you were watching on YouTube, thank you so much for coming out, and we hope to see you around soon.